It's nice. You just press
Okay.
the whole car is like hot. Yeah.
So
I don't even know if that would work.
today we're going to look at going backwards.
Oh boy.
Well, this will maybe help you and then also confuse you.
I can't even go full. That's a good one.
Okay, so what I'd like you to do is try to come up with the original function that yields the following derivatives. Okay, so I'm going to give you 6 things. So use what you know about derivatives and try and kind of work backwards.
We're getting one original function.
So for example, if capital F prime of x is 2x, I want you to come up with what the original function, actually I should use the capital F there. Okay, what's the original function? Okay, and then so on and so forth. I'll give you just a few more here. Nah, just because. I mean, well, kind of, but nothing we need to worry about right now. If you want to use the lowercase, I guess that's fine.
How can you be sure?
All right. So there they are, all 6. Give it a go.
You're forgetting a crucial point. For which one? Well, well, they'll explain the point you're missing. Is it something I should know? Well, think about a derivative, right? If it's like x plus 5, like x squared plus 5, right? Yeah. The derivative is 2x, right? Yeah. So that constant just disappears. So what does that mean if you go backwards? You could have any constant, right? Yeah. So you denote that by saying c.
That is correct.
I read like the first 5 pages of the integration.
Oh. Tricky.
Okay. Let's call on some people here. Let's go to Connor, number 1.
X squared.
X squared. Okay. Yes. The derivative of x squared does yield 2x. Very good. All right. Ryan, number 2.
2x cubed plus c.
Oh, 2x cubed plus c. Okay, what's c?
That is a constant.
Okay. So that's true, right? If we took the derivative of this, 6x squared, and then the derivative constant is 0, so it disappears. Yeah, that's right.
Every answer after that's going to have C in it now.
Do you have to put plus c? No, not with the question that I asked. No, you don't have to. You don't have to. I mean, it's not wrong. It's not wrong. Jack, number 3. What thing we take the derivative of that gives you cosine? Sine. Yeah, sine. Sine of x. Okay. All right. Listen up, please. All right. Joe.
Who?
Joey.
Oh.
What do you say here for number 4?
E to the x minus 3x.
E to the x minus 3x. That works. Okay. Donovan, how about this one? Arctangent of, sorry, x. Yep, arctangent of x. Very good.
Now the stakes are high because there's no colon again.
Sorry? For which one? For number 5? Okay, what did you say?
X over 1 plus x.
All right, so let's look here. So if I do the derivative of that, it's going to be 1 plus x bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Yeah, not quite because it's a quantity squared. So no, good thinking though. Good thinking. I'm glad you looked for that. Yes, but in fact, this one, it does not work out. Okay. Thank you for offering though, Brandon. It's good to check. Okay, that's good. I'm glad you tried that. Christian!
I don't know.
No idea. Okay, this one is a bit tricky. Emma's got it? Okay, very close. -5 times the ln of 2n minus 5x. So be careful here. Okay, -5 natural log means the -5 is still going to be there. What's the derivative of natural log of something? 1 over that something times the derivative of what's inside. So times -5. So do we need this -5 out front? No. So it's just natural log of 2 minus 5x. Okay. All right? All right. If you did any of these successfully, you just did integration. Okay, and that's what the next thing that we're going to be looking at today, antiderivatives. Okay, so let's kind of then analyze what's going on here with that. All right, so let's get more formal now. So that was a little, just to see that you can do it. Okay, but now let's get into a little more formal stuff. So the function lowercase f, function capital F. Function capital F, okay, and yes, and now this is like kind of have some meaning for a reason why we do capital F. The function capital F is an antiderivative, okay, of f of a lowercase f, exactly right. So the function capital F is an antiderivative of lowercase f on an interval I if capital F prime of x is equal to f of x for all x in that interval I that we talked about. So capital F is an antiderivative of f. Capital F is an antiderivative of lowercase f if we take the derivative of capital F and it's equal to f for all the x values that are in I. So if it's the same thing as lowercase f, if the derivative of capital F is the same as lowercase f, for any x that you pick in your interval there, then we say that this thing, f, is the antiderivative of f.
So basically,
It's like the backwards derivative.
so f is an antiderivative if capital F is an antiderivative, if lowercase f is its
Is
derivative.
its derivative, yes, basically, or is equivalent to its derivative, yes.
Okay.
Yep, exactly right. So I'll repeat that one more time for those of you that, maybe trying to, I know it's weird because we're going backwards now. Capital F is lowercase f's antiderivative if capital F's derivative is equivalent to just f. Okay, if f is the derivative of capital F, basically,
So,
or equal to it.
can you go back up and show us the contour of the things we did?
Yep. So, for example, capital F here is e to the x minus 3x. It is the antiderivative of e to the x minus 3 because its derivative is e to the x minus 3. So you could call it, instead of saying this is capital F prime of x, we call that lowercase. We could put a lowercase f there if we wanted to. I chose to do it this way because we weren't, we hadn't seen the capital F lowercase f kind of deal. And in general, this is sufficient too. This is fine as well to kind of see it this way. Okay, so does that make sense? You need to see another one? You're good. Okay, so that's the basic idea. Okay, so capital F is an antiderivative. It is an antiderivative rather than the antiderivative. Okay, and do you guys understand the point I'm trying to make there? There could be more than one antiderivative, okay? And you might think about yourself, oh my gosh, how many different options are there? Well, there's an infinite number of antiderivatives, but you'll see what I mean by that, because all the different constants it could be, right? There's not going to just be one antiderivative for a given function without more information given. So f is an antiderivative rather than the antiderivative because, as was kind of described earlier, because any constant c may be added to capital F. Okay? Any constant c can be added to that capital F, and it would still have the derivative of lowercase f. So let me show you an example of that. So here's an example. Okay, so we want to, I think I'm like way zoomed in there. There we go. Okay, so let's say we want to find the derivative of the following. This is an example of that statement I just made there, or we just wrote down, to really just drive the point home here. Okay, so let's say we want to take the derivative of these three functions.
Take the derivative.
It says find the derivative of the following. So not antiderivative, we got to be real careful now, right? Because now we've always just been taking the derivative, but now we can go forwards or backwards, and we got to be careful what the question's being asked. We're asked to find the derivative. That means I want to find f prime for number 1. I want to find f prime for number 2. I want to find f prime for number 3.
Oh, interesting. What a twist.
Okay. What is the derivative of x squared? Let's go to Maya. 2x, you got it. All right. Maya, what's the derivative of x squared plus 5? 2x. Maya, what's the derivative of x squared minus pi to the e? That's it.
Forget the s.
Thank you.
That's it.
That's it, just 2. What do we notice about the derivatives of these three functions?
They're the same.
They are exactly the same. Okay, so 1, 2, 3 are all antiderivatives of what?
X squared plus C.
So x squared plus 5, and x squared minus pi e, these three functions that we started out with, they are all antiderivatives of the same thing. They are all antiderivatives of what?
2x.
2x. Okay, 1, 2, and 3 are all antiderivatives. So f of x equals x squared, f of x equals x squared plus 5, f of x equals x squared minus pi to the e are all antiderivatives of 2x. Okay, we represent all the antiderivatives, because there's an infinite number of possibilities. We represent all antiderivatives of 2x by x squared plus c. Okay? This thing is known as the general antiderivative. And why do you think we call it the general antiderivative? Ryan?
Because it will cover all of these derivatives.
Yeah, all the possible it represents all the possible antiderivatives of 2x in this case. It's all possible. Okay. Later we'll look at finding the specific antiderivative of 2x. And all that requires is just being given a piece of information, a point, to then figure out what the c value has to be. Okay? All right. Scooting up here. The constant c, and c is like the typical variable that we use for that. The constant c is called the constant of integration.
It's going to get very confusing in physics when c goes from a constant to the speed of light.
They might actually not.
Speed of light is constant.
Yeah, they might actually not use that because we use calculus in
Okay.
physics.
Another name.
Generally denoted as the speed of light.
So another name, besides calling c the constant of integration, or sorry, another name for the general antiderivative, another name for the general antiderivative so besides calling this thing the general antiderivative, x squared plus c in this case, for example, it is also the general solution of the differential equation. Oops, I wrote the word the twice. The f prime of x equal to 2x. A differential equation. And we'll look more at differential equations later. But basically, a differential equation is an equation that's got derivatives in it mixed up with other variables. You can see in this, we have an equation. It's got an equal sign, right? It has variables x, but it also has a derivative in it as well. Okay, but this thing here is also called the general solution of this differential equation, right? If you solve this differential equation, if you go back to f, you get x squared plus c. Okay, we're almost done. I have one more little thing I want to show you, and then we'll look at some generic, some specific differentiation formulas or integration formulas and stuff like that. Okay, so. Okay, the operation. So, like the operation of, when you use the plus sign, we have the symbol for addition. It's the plus sign, right? We have the symbol for multiplication. It's the times sign, right? So on and so forth. The operation of finding finding all solutions. Bless you. To a differential equation. Again, a differential equation just has a derivative in it. The operation of finding all solutions to a differential equation is called antidifferentiation. So like that's what we did when we took the derivative 2x and we came up with its antiderivative, x squared plus c. That's called antidifferentiation. It's like, backwards differentiation. Okay? Or a synonym for that is called indefinite integration. Okay, and that's the word integral and all that good stuff too. So antidifferentiation, indefinite integration, same thing, and is denoted by the integral sign, which is the weird S thing, or F, or whatever you want to call it. Okay, and it looks like this. Okay, it's in quotes. It looks like something like on a piece of music. Okay. So the general solution is time to wake up, Drew. No, snooze it. That's why you have several alarms, I'm guessing, right?
Yeah, I was turned them off and I was even thinking about it.
Done?
Oh my god. I snoozed it.
Okay, so well, the time is up, so I'll give you like another minute if you want to like quicker. Okay.
Famous last words. Famous last words. Hey guys, watch me try this. Hey guys, watch this.
Hold my beer.
Yeah, hold my beer. Hold my beer is favorite last words. Yeah, last words.
Okay.
Who needs seatbelts?
So you can read this as the antiderivative of f with respect to x. Okay, you could also call this the indefinite integral of f. With respect to x.
So it's basically like the dy dx of antiderivatives.
The one second, sorry. The indefinite integral of f with respect to x. Okay. So yes, just like when we take the derivative, we can take the derivative with respect to x, we can take the derivative with respect to y, we can take the derivative with respect to t. It depends, kind of on what variables we have and what we're looking to do. In general, 90% of the time, when we took the derivative, we were taking the derivative with respect to what?
X.
X, right? It was the derivative of y with respect to x. In this case, when it deals with functions in a similar fashion, similarly, 90% of the time our functions are going to be with x's, and we'll integrate with respect to x. If, however, for some reason, for example, t is a common variable, right, you could integrate something with respect to t, because if it's like, a velocity, and you want to get a position, you integrate the velocity with respect to t, gives you the position. Stuff like that. Okay, questions on anything there? I know it's a lot of, vocabulary and terms and stuff like that. We haven't done a whole lot of, calculations or anything. We're going to do that right now. So, pass out these.
Is that it for our notes?
Well, this is kind of part of notes,
Okay,
too.
but notes.
That's like the note-taking in the paper, yeah.
Hey, there's a big table of these in the
I don't remember any of that.
How's Kansas? Remember?
Oh yeah, I don't remember it. I remember.
Taking the derivative.
Just, I was going to say your note pasting is really nice.
My what?
Like how you paste your notes.
Yeah.
I was just thinking about how Mr. Daly, he has no Mr. Daly does notes.
Does he use PowerPoint?
Yeah.
see, I'm writing them along with you.
Yeah.
That helps. That's why I do that.
He talks like a mile a minute.
Right. That's why I do it. It forces me to slow down for you guys. That's why I write them out.
Yeah, he does.
Isn't a mile maybe 60 miles an hour?
Yeah.
That's a funny question to ask people. It's like, if you were traveling 60 miles an hour, how long will it take you to travel 60 miles? People are like, well, let me carry this thing.
Okay, so we're gonna come up with our differentiation rules here. In fact, go ahead and just take 2 minutes to fill in those differentiation rules. I'll help you out with a little bit of these here. So, for example, the derivative of kx, k is a constant, remember? So, derivative of kx is k, right? The derivative of k f of x is going to be k f prime of x. Again, this is not surprises. This is stuff that we've already seen. Okay, the derivative of f of x plus or minus g of x is going to be what? F prime of x plus or minus g prime of x. So go ahead and fill in the rest of those. You don't have to worry about, well, I'll do the a to the x one because we didn't talk about that one, but natural log of a times a to the x. Okay. X to the n.
Tangent is sine squared tangent. I don't remember.
That's right. We don't.
It's secant squared. So cosecant and cosecant cotangent? No, it's negative cosecant cotangent. Yeah.
Looking it up.
Negative cosecant cotangent.
Here.
Boys. On the other page. Oh, never mind, just kidding.
Secant is secant tangent.
Hold on. Cosecant cotangent. Isn't it negative cosecant cotangent? Or cosecant of x?
Yes.
And then cotangent is negative cosecant squared times x prime.
Is A a constant?
He has it written on the board. I want my camera.
Yeah, I gave that one to you.
Don't write on that, I'm framing. Don't write on
Yeah, the carbon fiber is like there's like one spot on the edge where I didn't get it exactly perfect. It takes me off to the camera look at it.
All right, Drew. Derivative of x to the n is? Yep, n times. All right, folks, back on track here. Derivative of x to the n is n times x to the n minus 1. Great. All right. Derivative of sine, let's go to Jack. Derivative of sine, Jack, is cosine. Okay. Derivative of cosine, Emma. Negative sine. Great. Derivative of tangent, Brittany. Secant squared x. That's right.
Aren't we forgetting the times the x prime?
Well, but this is with respect to x, okay. It's times 1. So, I mean, you could put a times 1 there if you want to. No, that's, yeah, not wrong.
So
Anna, derivative of secant. So derivative of secant is secant x tangent x. Secant x tangent x. Okay. Brandon, derivative of cosecant. Negative cosecant x, cotangent x. All right, very good. Derivative of cotangent, let's go to Chanda. Negative cosecant squared of x. Very good. Derivative of e to the x. Austin.
E to the x.
You got it. Toughest one there is. All right, there we go.
This is the first time we pulled on, I think.
And then derivative, derivative of natural log of x. Austin.
Yay! Natural log of x is 1 over x.
1 over x. That's right. Okay, very good. Yeah, I don't know. The calculator's not very good at doing random numbers sometimes, so I blame the calculator.
It's truly random, but
it's not. You can't program something to be random, so or not truly random.
Yeah. And everybody was saying that I was, yeah, I know, because everybody was saying that I was
Now.
wrong.
With this kind of formula, then if this is true, the derivative of this gives us this, then if I integrate k with respect to x, what should that equal? Again, if I take the derivative of kx and it gives me k, then if I integrate or do the antiderivative of k, what should I end up with? Kx. But plus a constant, right? Because the derivative of that constant would be 0, it would disappear. Okay? If I integrate k, f prime of x, dx.
Oh, not the dx.
Oh yeah, don't forget the dx's, folks. Do not leave the dx out. What is it? It's showing with respect to x. We're integrating this thing with respect to x, kx plus c. So it's necessary. If I put a k, if I put a dt here, then it'd be kt plus c. So you want to make sure that you put the, put something there. All right. If I integrate
the second one.
Oh wait, you're right. I did not. Sorry. K, f of x plus c. Thank you. Okay. Okay. F prime of x plus or minus g prime of x
Should there be a k?
with respect to x.
Should there be a k?
For this one, there's no k here.
But, so, do we only have to distribute the dx? Should we put, like, f of x plus or minus g of x in parentheses?
Yeah.
Okay.
Yeah, you can put it in parentheses if you want to, like this.
Okay.
So here's the thing. I understand what you're saying, Austin. So with the Austin's question was, do I need to put parentheses around this to kind of show that the whole thing is integrating with respect to x? The idea is that this is kind of like a group. Like this is kind of grouped if it's between the integration symbol and the dx there. It's grouped together as one thing. You don't need the parentheses there. It's grouped together as one thing. That being said, though, the integral, we're taking the integral of a sum now, but that's equal to the sum of the integrals. Just like when you take the derivative of a sum, you can take the derivative of the individual pieces and then add them back together. Same thing here. You can take the integral of the individual pieces and then add or subtract them back together, and so it ends up just being f of x plus or minus g of x.
Plus or minus c.
Not plus or minus, just plus c. The minus we don't need to worry about because, again, the constant could be positive or negative, so it doesn't matter. You don't need plus or minus c, just plus c is fine, and then c could be positive or negative. So good point, but that's, yeah. All right, and so we can kind of like continue on here, right? The integral of n times x to the n minus 1 with respect to x is just x to the n plus c. Okay, but this is not the normal one that we see. This is not the normal rule that we see. All right, so I want to kind of like separate that here. All right, this is not the normal rule. The normal rule that we see is if we integrate x to the n, well, now what does that become? So, right, we're going to have x to the n, not minus 1, plus 1. We're going to add 1 to our power now. Right? And then out front, it's going to be 1 over that n plus 1.
Oh, man. 1 over?
Uh-huh.
Oh, I got it. Got it colored in.
Sorry, Anna? Is this one right? Yeah, oh, absolutely. This one's still right. But the more useful one, the one you're really going to want to have down, is this one. This is the one we want to be comfortable with. So when you take the derivative, what do? You bring the power out front, lower the power by 1. Now we're going to add 1 to the power and have 1 over that new power out front. Because why does that work? Well, if you take the derivative of this thing, what's going to happen? N plus 1 comes out front. It'll be n plus 1 over n plus 1, 1. And then subtract the power by 1, x to the n. So it does give us x to the n like we should get there, going backwards. If we take the derivative of this, we end up with x to the n. So this is the one you really want to have down. I'm going to box in this one, because that's the one you really want to have down. All right. All right, integral of cosine of x with respect to x. And we'll see more of that here in a second. Integral of cosine of x with respect to x is? Sine x plus c. Integral of negative sine of x with respect to x is? Cosine x plus c. Integral of secant squared. What's the integral of secant squared? Tangent of x plus c. Integral of secant x tangent x with respect to x. Secant of x plus c. Notice what's missing here. I don't have an integral for tangent by itself yet. I don't have an integral for secant by itself yet. I don't have an integral for cosecant or cotangent by itself yet. We'll look at those later, but right now we don't know how to integrate tangent of x. No idea what the integral of tangent of x is. All right? Integral of negative cosecant x cotangent x with respect to x is cosecant x plus c. All right, integral of negative cosecant squared of x dx is cotangent of x plus c. I don't know if I need to box all those in, but there they are. I don't know if it's really helping at all. Integral of, okay, here's an easy one. Integral of e to the x dx is?
E to the x plus c.
Oh, thank God, an easy one. Okay. Integral of the natural log of a times a to the x. Again, don't worry about too much about this one. We rarely ever will see it. A to the x plus c. And then the integral, now here we go, the integral of 1 over x, which, by the way, is the same thing as the integral of x to the negative 1, right? Isn't that equivalent? That's equal to the natural log of the absolute value of x plus c. Okay, there they all are. All of our integrals that we know from our basic derivative rules. That's all of our integrals that we know from our basic derivative rules. Okay. Questions on any of that?
Should the fourth one again? The one with the end of the x to the n? If you like zoom in, I can't tell what that is. It's 1 over n.
1 over n plus 1 out front, that's the coefficient, times x to the n plus 1. You done with that one? All right, you ready for the next one? So you don't quite have 15 minutes. So would you prefer me to call you for flex, and have we finished there? The last one. Yes, you need the absolute value.
How do you get that? Is that just what it is, or is there a way to figure that out?
It basically is what it is. The idea is you don't want to end up taking the natural log of a negative number, so you just make it absolute value there. Because you can't take the natural log of an absolute value, or you can't take the natural log of a negative number. Okay. All right, flip this paper over. Why put an absolute value there? Because you, yeah. All right, so just like when we first started derivatives, right, we had a very limited set of rules and things that we could use to take those derivatives. Remember, we had to really rewrite things before we could take the derivative. In a similar fashion, right now we have to be able to rewrite things in a form that we know so that we can then take the integral of it. So, for example, and this is very important, the most important step in integration is rewriting the integral in a form that fits the basic integration rules that we know. So we want to rewrite each of the following before integrating. So, 1 over x cubed. Now if I look over here, if I want to integrate 1 over x cubed, the only thing that's like even close to that is 1 over x. But is integrating 1 over x the same thing as integrating 1 over x cubed? No. So the integral of 1 over x cubed is not natural log. No. No. The only thing that you integrate to get natural log is 1 over x. The integral of 1 over x is natural log. So how can we rewrite this then to get something that we can take the integral of? Yes, right?
X to the negative 3.
X to the negative 3. There it is, rewritten. Okay, x to the negative 3. So if we rewrite it that way, which rule can we now apply?
X to the n dx equals...
Yeah, the fourth one down, this one right here. This now rewritten as x to a power. And so what's that integral going to be?
It'll be...
We're going to take that negative 3, and what's that become?
Negative 1/2 x to the negative 2.
That's right, it's negative 1/2 x to the negative 2. I'll tell you in a second where that came
Plus
from.
C.
Plus C. Let's go back to our rule here real quick, because I was asked, where does the negative 1/2 come from? It's x to the negative 3 right now, right? So n is negative 3. When we integrate that, our x becomes x to the negative 2 then. You add 1 to negative 3 and you get negative 2. We're adding 1 to the power. And then you divide, or you have 1 over then that new power out front. Okay, so you add 1 and then 1 over that new power out front, plus C. Now it says simplify it. What does it mean by simplify it? Well, normally we don't like to leave with negative exponents, so I can rewrite this as negative 1 over what? 2x squared, and then plus C. Okay, that is the final answer there. All right, questions on any of that? Okay, shall we try another one? And then we'll stop after this one, okay?
Okay.
We'll cool it after this one. All right, the next one we've got is integral of 1 over 2 times the square root of x. 1 over 2 times the square root of x. All right, how should we try to rewrite this one? Can't use e, can't use the natural log. It's not 1 over x, it's 1 over the square root. So, yep.
Alright, so I'm going to first rewrite it as 1 over 2x to the 1/2.
Okay.
And I'm going to do 1/2 x to the negative 1/2.
So change the square root to x to the 1/2, just like we had to do for derivatives. Okay, so there it is. All right, when we integrate x to a power, what do we do with our to get our new power? What do we do?
You add 1.
To get our new power, what do we do? Add 1. So negative 1/2 plus 1 becomes x to the 1/2. That new power goes out front, but it's in a fraction 1 over 1/2.
2.
Yeah, 2. And we still have that 1/2 from the original integral there as well. Okay, so the 1/2 is from the 1/2. This 1 over 1/2 is from integrating the x to the negative 1/2 to become x to the positive 1/2, 1 over that. Let me do it this way. Integrating x to the negative 1/2, let me block it off here. Again, integrating x to the negative 1/2, you add 1 to your exponent. So negative 1/2 plus 1, 1/2. But then you have to put 1 over the new power out front as well for part of our integration there. We still have this 1/2 coefficient, though, that's there, so we're going to put that one out as well. And so then this becomes
X to the 1/2.
1 over 1/2 is 2. So the 2 and the 1/2 simplify to just 1. So it's really just x to the 1/2 plus c. Or if you want, you can say the square root of x plus c. Yes, in a sense. We're undoing the chain rule.
Breaking the chain.
Breaking them chains.
That's a song by Dawkins. Ever heard of that band?
Dawkins?
80s, like hair metal thing.
Break the chains.
Yeah.
Interesting. All right, we'll stop there. I'm going to give you guys an assignment tonight.